Welcome to the Stuffler Broadcasting System again. And this is your lifeline for Chapter 6. It's continuous probability distributions is our topic. And this can be pretty challenging and a little bit difficult to get used to. It's a really important chapter, so I hope this slideshow and video will help. Topics that we're going to cover, we're going to look at, first of all, what is a continuous distribution, what are its attributes and characteristics. We're going to look at something called the normal distribution, something called the standard normal distribution, and we're going to use the standard normal distribution to approximate the binomial. There's one really important piece that you need to understand during this particular presentation, and that is the application of something called the continuity correction. And it's a little bit difficult to get to know. We'll also do the uniform continuous distribution, which I'm sure you'll find is pretty easy. So, anyway, let's get started. So when we're talking about continuous variables, you know that a continuous variable includes decimal places. It's not integers. And as such, we could say that these variables are intervals. And we're going to be looking at them as probabilities or areas underneath curves. We've done the discrete variable, and in the discrete variable, every value of x has its own probability. Well, continuous variables are different because there are an infinite number of values for x. So, the characteristics of a normal distribution. Well, this is called a probability density function. And here's our normal curve. Underneath this bell-shaped curve is area. And this area is what becomes our probabilities. Now, you might notice that at the bottom of this particular graph, it shows mu plus 1 standard deviation, 2, 3 standard deviations. Again, the mean, mu, minus 1, 2, and 3 standard deviations. So it is a symmetrical curve, and I'm hoping that you might know why we have these hash marks at plus 1, 2, and 3 standard deviations, the same for minus 1, 2, and 3 standard deviations. And think about that. There are certain characteristics of the standard normal distribution. It's, first of all, you have to realize that for every mean and standard deviation, there's going to be a different normal distribution, a different curve. So because of all these different values that the mean and standard deviation can take on, we need to transform our variables. And the way we do that is we transform them to a standard normal distribution based on a mean of 0 and a standard deviation of 1 using the formula, well, that's our z-score formula. So z is equal to x minus mu over sigma. You've done it before, and you're going to be doing it quite a bit during this particular chapter. And again, the whole purpose is calculating a z-value is to standardize whatever data values we're working with so that we can calculate the probabilities or the areas under the curves. So when we're looking at z's and these distribution, the standardized normal distribution, it has a scale from -3 to +3. That means we're going to get a z value that's in that range. The area under the whole curve has to be equal to 1. If we were using calculus, then we could get the probability of a particular event by taking an integral or through integration. We're not going to do that. We're going to do this approach a different way. So here's my what we call probability distribution density function, and this happens to be miles per hour. You can see the highest point or the mean is at 75. Then there's these breaks at 5 intervals of 5 going either side of the mean, and those are the standard deviations. The standard deviation here is 5. Total area under the curve is 1. The mean, the variance, and the standard deviation basically reveal the shape of the distribution. Now, if my variance or my standard deviation, instead of being 5, was 2.5, I would hope that you would understand that this distribution would have a very different shape. It would tend to be not so widely dispersed and appear taller. Obviously, if the standard deviation was something greater than 5, it would be just the opposite. It would be a flatter mound and more widely distributed. So did you think about that question I asked you about why are the breaks, the intervals below the normal distribution or the standard normal distribution, +1, +2, +3, -1, -2, -3, and that's all because of the empirical rule. Remember, when data are normally distributed, we expect 68% of the values to lie within ±1 standard deviation of the mean, 95% of the values to lie ±2 standard deviations away from the mean, and 99.7% of the values to lie between ±3 standard deviations from the mean, and that's shown on these graphs at the bottom of the slide. So you need to get used to this curve. Remember that first of all, the total area under the curve, all of this area, is equal to 1. The middle, well, the middle is the highest value. That's our mean or our average. Highest meaning the highest point of the curve. The area to the right of the mean. Okay, I'm not real good with right and left, but this is the area to the right of the mean. If this whole area has a value of 1, then this area to the right of the mean has to have a value of 0.50. And right now I'm going to caution you on something. Whenever you're working with area, which is really probability, use 4 decimal places. It's just a real good habit to get into. So I'm going to restate that. This area on the right side of the mean is 0.5000. Obviously, the area on the left side has to be 1 minus 0.5000 or 0.5000. So area to the left, area to the right of the mean. And I have asked this question. And this question asks, what is the probability of driving faster than 78.5 miles an hour? What is the probability of driving faster than 78.5 miles an hour? Well, you know, I drew in this dashed line to represent 78.5 miles an hour. The reason I drew that in is because you need to be doing the same thing when you're first learning continuous distribution problems. Draw the bell curved. Draw in the mean once you're given that from the data. And then draw in the x value. The x value is where you're being questioned about what is the probability of driving faster than 78.5. Well, I'm going to say this is my 78.5. And now what I'm looking for is this probability or this area under the curve beyond 78.5 miles an hour. So we can use what's called standard normal tables or Excel Megastat to find this probability. I'm going to ask you for this case to turn to your appendix, table 3, or you can just look in the back flap of your book and you'll see the graph that says, or the table that says cumulative areas under the standard normal curve. And it's in your appendix, it's labeled table A3. Now, to learn how to use this, I've asked you to, as an example, find the probability that, well, you know what, I want to change this. Ignore that 0. I want to find the probability that z is less than 1.96. So again, I'm going to change that. Probability that z is less than 1.96. Now, when you're looking at your table on A3, it says cumulative areas under the standard normal curve. First of all the numbers inside the table, that's the areas or the probabilities. Those 4 decimal place values. Then on the left column, you have Z measured, and across the top, it also measures Z. So what I'm asking you is to find the probability that Z is greater than 1.96. So you're going to go down the left-hand side column, find 1.9. Then you're going to go over until you get to that column that says 0.06, and you're going to have the answer. So what is the answer? What is the probability that Z is greater than 1.96? Well, the answer you're given is 0.9750. If you look at the top of your table, you'll see that the shaded area, now mine is shaded in blue, is to the left of the Z value. Well, the Z value we just looked up is 1.96. So if I ask you find the probability that Z is less than 1.96, then that's what our table is telling us. If the probability is 0.9750, or there's a 97.5% chance that Z will lie below or less than 1.96. Or values. Another way to say that, remember, 1.96, that's the number of standard deviations. A value lies away from the mean. In this case, it's above the mean because it's a positive number. So that means that 97.5% of our values we would expect to find below or having a Z value of less than 1.96. Now, this particular graph shows between 0 and 1.96, that probability is 4750. So where do you think that 4750 came from? Remember, the table gives a value of 0.9750 for all the area to the left of 1.96. This half is 0.5000, which means this area between 0 and 1.96 has to be the difference between that and 1. So you just take 0.9750 minus 0.5, and you will get 0.4750. So now you're asked the second question. Now find the probability that Z lies within negative and positive 1.96. Well, that's a pretty easy one because of symmetry. Because of symmetry, it's the same. And an easy way to see it here is if this is the mean, this is our negative Z, negative 1.96. The area under this curve is 0.4750. We've already used this one, 0.4750. And so the probability that Z gives us a value in between negative and positive 1.96 is the sum of those two 4750s, or 0.9500. So 95% of the area, or there's a 95% chance that a Z-score will lie between negative and positive 1.96. So we're still getting used to this curve. Remember the earlier question that I asked you? I said given a mean speed of 75, a standard deviation of 5, and those are miles per hour, what is the probability of driving faster than 78.5 miles an hour? So we can go to Megastat and do that. I need to escape from this. I'm going to go to Add-ins, Megastat, Probability, and I'm going to scroll down to Continuous Probability Distributions. Now, well, this is an old one I did, so let me clear it. The mean mileage, the mean miles per hour was 75. The standard deviation was 5. And I want to know what's the probability that of getting a result that'll be greater than 78.5 miles an hour. So what we're doing is we're calculating the value, the probability, P, given an x value. Here's my x value. We can also do the opposite, but for now, we're calculating probability. So let me hit OK. And here's our output from Excel. Shows the mean of 75, the standard deviation of 5, the x value that I use, 78.5. It shows our z-score. What this tells us is the value 78.5 lies 0.70 standard deviations from the mean. Being that it's a positive value, that means it's above the mean or to the right of the mean. So again, the question was, what's the probability of having a speed greater than 78.5 miles an hour? You've got two answers here. Since we're asking about greater than 78.5, then this is the upper value we need. This is telling us there's a 24.2% chance of getting a driving speed greater than 78.5. What this lower value tells us is the probability of getting a driving speed lower than 78.5. So what this tells you is there is a 75.8% chance of getting an observation where the driver will be driving at less than 78.5 miles an hour. Okay, so let me return to the slides. So it doesn't matter if I would have done that problem using the table, A3, or Megastat. I'll get the same result. Now there's another way that we can use this table, and this is where things get kind of confusing. And that is we can use the table to find the z-value for a certain probability. It's kind of the inverse of what we just did. And let me use an example. What z-value defines the top 100% of a normal distribution? What z-value defines the top 1% of a normal distribution? Okay, so pick up your book with your table, and now we're looking for a z-value, and what we have instead, or what's given, is the probability, 1%. So, you know, the probability of 1%, if we were to write that out in a proper form, it would be 0.0100, using those 4 decimals for probability. So we can't look up the tail area in this book. We can look at the area to the left that we're looking for the z that'll give us the area to the left of, well, not 1%, but 0.9900%, or not percent, 0.9900. So look in the body of the table, find the closest value to 0.9900, and then tell me what z-score that would be. Again, you're looking for, in the middle of the table, you're looking for the closest value to 0.9900. And if you look, you'll find that that's associated with a z-score of 2.33. So a z-score of 2.33 is the top, gives you the top 1% of a normal distribution, meaning that any z-value that is greater than 2.33 falls in the top 1% of the normal distribution. So we can also do this using Megastat. And I have one little thing I want to add here. This implies that 99% of the area to the left of z, 2.33. And again, we found that by looking for an area of 0.9900 in the table. But again, let me escape from this and go to Megastat. And I'm going again to probability, continuous, and I'm going to clear this because it gets a little confusing. Now what we're going to do is we're going to calculate z given p. And since we're working with z, then that's the standardized normal form with a mean of 0, a standard deviation of 1. Our probability, the probability that we want to know is 0.0100. And you can click OK. So, again, we've got the same result. This says that the region, or the probability above our z-value of 2.33, that probability is 1% for a z-score of 2.33, which also means that for any z-score below positive 2.33, that probability is 0.9900. So again, this is an inverse way. I know this is a little bit confusing, but again, when you get problems like this, you have to ask yourself, am I being asked probability or am I being asked z-value? Z-value, remember, is the number of standard deviations. A value lies from the mean, and it's 2 decimal places. A probability is 4 decimal places, and it's the area below the standard normal curve. So let me return to the slides again. Okay, we did that one. We've done this one. And this gives you the instructions. This particular slide gives you the instructions on how to do it using the table and how to do it using Megastat. Here I've said look for the area of 0.9900. If you look for that area, you know what? It's going to give you the reverse. So you really should look for 0.0100. Looking for 0.9900, what will that give you? What z-value will that give you? Or maybe I should ask, where will that z-value lie? If we look up this area, that z-value will lie to the left of the mean. You'll have the same value, but it'll be negative 2.33. Okay, here's another example. Suppose John took an economics exam and scored 86 points. The class mean was 75. There was a standard deviation of 70. What is the probability of scoring as high as John? First thing I always will ask you to do, and I know many of you won't do it, but believe me, when you're first learning the normal distribution, you really need to draw a graph. All you're going to do is draw a normal curve. You're going to draw the mean that's given, in this case 75. Then you're going to draw the other information that you're given, which is an x value, and that x value is 86. So, after you've put 86 in, which obviously is going to be to the right of 75, the area that you're wanting to look for is shade that area above 86. Rewind. What the question's asking, what is the probability of scoring as high as John? So you're gonna shade the whole curve to the left of 86. So once you've drawn your graph, then you'd calculate your z-score. You could go to the table to determine the probability, or you could go to Excel using Megastat to calculate the probability. I'm just calculating the z-score here by hand because, as you know, Excel doesn't easily calculate a z-score. It's not like we get a easy command and we could say calculate z. But anyway, the z-score comes out 1.57. So what in the world does that 1.57 mean? First of all, it's positive. So it tells us, again, the number of standard deviations away from the mean that John's score was. His 86 was 1.57 standard deviations from the mean class score. And once we know that z-value, then we can get the probability of scoring as high as John, meaning up to and including 86, or greater than John. Guess I have a duplicate slide in here. And the probability of scoring of as high as John is, well, if you look it up, you get 0.9418. Either look it up or you do it in Excel, you'll get 0.9418. So there's a 94.18% chance of scoring as high as John, which means 86 or less. John also then means he's approximately the 94th percentile. And here's what your 94.8 looks like on your graph. This is the shaded area you should have had on your bell curve. Again, you can use Excel to compute these probabilities. And for Excel, Megastat, here's what is the probability of scoring less than 86. You go into Megastat, probability, continuous probability. You'll enter the mean 75, the standard deviation of 7, and then the X value of 86. And I've asked you this other question. What is the probability of scoring higher than John? Well, the probability of scoring higher than John is 0.0582. How in the world do you get that? Well, let me go back a slide or two. If we got the probability of scoring at least as high as John was 0.9418, how do we get that one? And the answer is we just subtract it from 1. So, not that you can see it too well, 1 minus 0.9418 tells us the probability of scoring higher than John. And in this case, there'd be about a 5.82% chance of doing better than John did on the exam. Here's another question, and this question says, and we're all relating back to John again, what is the probability of scoring exactly 86? There's a problem here. I'm asking you what it is. The problem is that 86 is a discrete value, meaning it's countable. And if we're looking at a normal distribution and we want to know the probability of scoring exactly 86, then we've got to answer another question. And that question is, where does 86 begin and end in a continuous distribution? Well, 86 begins and ends at 85.5 and ends at 86.5. So in order to determine the probability of scoring exactly 86 using a normal distribution, then we have to determine the probability of getting a score from greater than 85.5 and less than 86.5. So it's a couple calculations. And I'm asking you should do that calculation using both the table and Megastat. Not that you could read that down here, but that's what I'm asking you to do. And so you'd be using two calculations, just as we've done before. And draw those two probabilities and the areas on your graph, and then you're going to take the difference between the two. And I've done it here on Megastat. I put in 85.5 as my X, my mean 75, my standard deviation 7. I got that 85.5 lies 1.5 standard deviations away from the mean. So to get a value of 85.5 or less, the probability is 0.9332. The second calculation, well, I threw in 86.5 is my X value. My mean is 75, standard deviation. My answer, Z value, came out to be 1.64, meaning that 86.5 lies 1.64 standard deviations from 75. And you can look it up on a table or just read it from this Excel output. And so the probability of getting an answer less than 86.5 is 0.9498. If you want to know exactly the probability of 85, then you take the probability of less than 86.5 minus the probability of less than 85.5, and that tells you the probability of getting a result exactly equal to 85 is 0.0166, or about a 1.67% chance, or 1.66% chance of scoring exactly 86 points on the exam. Now remember, whenever you're using the standard normal distribution or the bell-shaped curve to calculate a discrete number, you must do the continuity correction. And if you forget that, you're going to lose points. So, there's another time when we might need to use the normal distribution to approximate the binomial. And remember, binomial probabilities, that's the one we just learned. And the binomial probability is the probability of success and failure is the same from trial to trial. There's a definite number of trials, and the probability doesn't change from one trial to the next trial. They're independent events. And so there are occasions where you will be asked, or it is required, or you should know when you have to use the normal approximation to actually calculate a binomial probability. And the reason that this happens, first of all, why this can happen, is because as n gets very large, binomial becomes more and more looking like a normal distribution. That's one reason. The other reason, there's a rule of thumb, and that rule of thumb says when n times p is greater than or equal to 5, or n times 1 minus p is greater than or equal to 5, then it's appropriate to use the normal approximation to the binomial. So, in this case, the binomial mean and standard deviation become like mu and sigma. So, again, n times p, again, that's a number of trials times the probability of success. If that exceeds 5, we use the normal approximation for the binomial. If n times 1 minus p, which means the probability of the number in the trial times the probability of failure, if that's greater than or equal to 5, if both of those values, n times p and n times 1 minus p, if they're greater than 5, then you must use the normal distribution to approximate the binomial. And that means, again, a continuity correction. So don't forget that. So, let's say that you have an n times p that's greater than 5. And you have to use the normal distribution to approximate the binomial. So, let's say if the question asks you, what is the probability that at least 17 people are smokers? Then where in the world does at least 17 begin? Where does 17 begin and end? Well, 17 starts at 16.5. So you would be using your x value as 16.5. If a question was worded, what is the probability that more than 15 people are business majors? Well, the probability that more than 15 are business majors, well, where does 15 begin and end? 15 ends, since it's more than 15, we can't include 15. 15 ends at 15.5. How about, what is the probability that fewer than 19 people voted in the last election? Well, 19. Fewer than 19 means you have to go all the way through number 18, and 18 ends at 18.5. So here's an example of a continuity correction problem that's required. It says, assume 500 IVC students are surveyed about whether or not they smoke or don't smoke. The results indicate that the probability of smoking was 0.45, and the standard deviation was 8.9. Well, the probability of smoking was 0.45, so how many students smoked out of 500? If you take 500 times 0.45, you're going to get, if I'm doing the math right in my head, 225 students. So remember, the requirement of whether or not you have to use the continuity correction is if n times p is greater than or equal to 5. Well, n is 500, p is 0.45, so 500 times 0.45 is way more than 5. The probability of not smoking was 0.55, so 500 times 0.55, which is our 1 minus p, is, again, significantly higher than 5. So then this is one of those cases where you would use the continuity correction. And the question asks, what is the probability that more than 275 are smokers in another sample of 500 students? So let me see if I did this, or okay, let me go ahead and go through this next slide. First thing you do is draw the graph. You calculate the mean, which is 0.45 times 500, and that should be 225. Then you'd need to, well, that should say third, and that should say fourth. But anyway, then you'd need to calculate the z-score using the continuity correction. And the continuity correction, since you're being asked the probability of greater than 275, then you would have to start with an x value of 275.5. Now, after you've done that, you could calculate your z. And once you've got your z, you can either look at the table or you can go to Megastat to determine the probability that x is greater than 275. And let me just go ahead and do that while we're here. And I'll have to get out of this slideshow. Go to Excel. I'm going to go to Megastat, probability, continuous. I'm clearing out this old stuff. My mean, well, my mean, if I did my math right, is 225. My standard deviation, what was my standard deviation? Do I know that from this problem? Let's see, I probably have to calculate it. Or was it given? Nah, let me find it. Oh, standard deviation was 8.9. Thank you. You don't have to calculate it. Okay. So standard deviation 8.9. And then the question was, what was the probability that more than 275? So we use 275.5 to calculate the probability. Again, 275.5. If you use 275 on a lab, you're wrong. Your answer is wrong. You have to use the continuity correction. Click OK. And, oh, my mean, okay, let's see what we got here. Whoa. it's an experiment. Okay, my mean is 225. Standard deviation is 8.9. My x value is 275.5. And my z-score is positive 5.67. So it's way out in the right tail. And so the question's asking, well, what is the probability that x will be 275.5 or higher? Well, the lower probability is 1, and then you can see this probability here is the upper, meaning greater than 275.5. So it's very, 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 very low. Okay, so let me go back to the slideshow. We have one more distribution to do, and that's called the uniform continuous distribution. I'm surprised your textbook uses a little different notational form. And, you know, every textbook, somebody might use a different letter designation, so mine is going to look different than the one in the textbook. So, the uniform distribution. Well, you know what? The good news, it's a rectangle, and you're just calculating area. So the uniform distribution is, for example, the value of x can fall between this value a and b with an equal probability. And so a is my lower limit, b is my upper limit, and then the height would be 1 over b minus a. And again, it's a real easy probability distribution to work with. You have these let me hide this. You have these characteristics. Its shape, symmetric with no mode. Its standard deviation. Its mean. Its cumulative density function. So we don't need to worry about this mathematical stuff. But there is one thing I do have to tell you, and that is, okay, why is my thing not advancing? So one thing I have to tell you, and that is that Excel will not calculate a uniform distribution. So that's something, either it won't do it in Megastat, it won't do it in Formula, so it's something that you just have to do. So I have an example. Banking transactions. Citibank management knows that the time to complete multiple transactions is distributed as a uniform random variable that takes between 15 and 30 minutes. So X is distributed in a uniform manner between 15 and 30 minutes. A is 15, B is 30. Find the mean and the standard deviation. Well, I went ahead and did that on the next slide. And so the mean comes out to be 22.5 minutes. The standard deviation comes out to be 4 1/3 minutes. And then you're being asked to find the probability that a multiple transaction takes between 20 and 25 minutes. And it shows you how to calculate this probability. And again, I'm sorry, but your book uses a different notational form than I use. And so what we're saying is the probability that a transaction is more than 20 minutes and less than 25 minutes. And the way you do that is you take the difference between the two and find out what proportion they are of the whole possible interval. And if you look at it, it comes out 33 1/3%. But basically, this is my A, 15, 30 is my B, 20 is my C, and 25 is my D. So all we're doing is taking the difference as a ratio or proportion of the entire distribution. So we're taking 5 divided by the difference, 15, or 33.3% of the distribution, or 33.3% of the probability. Okay, well, I hope that helps you get through this next chapter. Believe me, you need to put some time into it. The continuous distributions are very, very important, particularly for what's coming in the future. So it's the better you know Chapter 6, the better you probably do on the next chapters. Good luck.